Hi everyone, this is part 4 of chapter 7. It's going to be the last video. We're going to talk about combustion analysis and do some problems. Let's get started. Historically, it was used to find carbon and hydrogen content of organic compounds by burning excess oxygen. As you see here in the picture, a partly combusted product is passed through catalysts such as platinum gauze or copper oxide or lead oxide, but anyway, it's passed through a catalyst at really high temperatures to complete the oxidation to carbon dioxide and water. After the oxidation happens, the products are then transferred over to these different traps. The first trap is your water trap. That is usually phosphorus pentoxide, which of course absorbs water. And then it goes through a chamber of ascarite, or basically sodium hydroxide on silica. That's going to be your carbon dioxide trap. So obviously the first trap is trapping the hydrogen, and the second trap is trapping the carbon. The increase in mass of each chamber actually tells you how much hydrogen and how much carbon respectively you have or you had in the initial compound. And then that guard tube, that last trap that you have there, prevents any atmospheric water or carbon dioxide from entering the chamber. So you don't want, because that's going to obviously alter your final answer. So you don't want anything from the atmosphere coming into your chamber, so they have that guard tube to kind of prevent that. But it's a very simple type of analysis. I mean, you have a sample, you want to test how much carbon and hydrogen you have in this sample, so you oxidize it, and then you put a water trap and a carbon trap. And then you measure the increase in mass of each of those chambers and relate it back to the initial sample by stoichiometry. Let's do a problem to see what we're talking about. So in this problem, it says a compound weighing 5.714 milligrams produced 14.414 milligrams of carbon dioxide and 2.529 milligrams of water upon combustion. Find the weight percent of carbon and hydrogen in the sample. Very simple. All we got to do is multiple ratios here. So if we have 14.414 milligrams of carbon dioxide, we know that our carbon only came from the carbon dioxide mass increase. So go ahead and convert the milligrams of carbon dioxide to grams of carbon dioxide. Then I go ahead and take that to moles of carbon dioxide through the molar mass. In 1 mole of carbon dioxide, I have 1 mole of carbon. And in 1 mole of carbon, I have 12 grams of carbon. The answer that you should get should be around 3.93 times 10 to the negative 3 grams of carbon. If you are looking in your book, realize that the numbers are a little bit different, or the answers are a little bit different, because I'm just rounding the masses, the molecular masses of carbon. They're actually using all of the digits for the molar masses, so I'm doing it the fast way. So I got 3.93 times 10 to the negative 3 grams of carbon. Okay, now I do the same thing for water. I know that all of my hydrogen is going to come from that water trap. So 2.529 milligrams of water, I go ahead and convert that to grams. I then convert that to moles of water. In 1 mole of water, I have 2 moles of hydrogen. In 1 mole of hydrogen, I've got about 1 gram of hydrogen. That ends up being 2.81 times 10 to the negative 4th grams of hydrogen. I'm almost done. All I got to do is find the weight percent. Weight percent is gram of substance over gram of sample. So my gram of substance for carbon was 3.93 times 10 to the negative 3 grams divided by the grams of the substance, which of course they gave it to me in milligrams. I just go ahead and move that over 3 spots. So it's 0.005714 grams times 100 is about 68.78%. And I do the same thing for hydrogen, I get about 4.918%. Again, realize the numbers are a little bit different from what you see in your book because I rounded off my molecular weights. But that's the procedure of how you do a problem like this. It's very, very simple. We're going to practice these in class a little bit more, but really we don't need to, because this is as simple as a general chemistry type problem. What about combustion analysis today? So like I said, historically it was to find carbon and hydrogen in compounds, but now they use combustion analysis to find all kinds of, or elemental analysis to find all kinds of elements or amounts of elements in different compounds. The most common one is what you see here. It's an elemental analyzer that uses GC, or gas chromatographic separation, to detect carbon, hydrogen, nitrogen, sulfur. Okay, and it's actually all measured in one run, in one trial, which is great. So here they put an accurately weighed 2 milligram sample in this little capsule, right? It just happens to be a tin or silver capsule. The analyzer is swept with helium gas that has been treated to remove any traces of oxygen, water, and carbon dioxide. So they basically flush the analyzer out with helium to make sure that they remove all traces and oxygen, because you don't want that to interfere with your analysis. So at the start of the run, you have a measured excess volume of oxygen, right? And that's added to the helium stream. Then that little capsule that has your sample in it is dropped into a preheated ceramic crucible. Really, really hot ceramic crucible, where the capsule obviously melts almost instantaneously and the sample is then rapidly oxidized. Those products pass through the catalyst, the WO3, which is tungsten oxide catalyst, to complete the combustion of carbon to carbon dioxide. In the next chamber, the metallic copper actually reduces the sulfur trioxide to sulfur dioxide and removes any excess oxygen that might still be there. But all this happens so that it could finally get to the GC. GC actually separates different compounds by their difference in retention time. And we're going to talk about GC later on in the semester. But basically, if you have, let's say, 4 different compounds, as you see here on the right, nitrogen, carbon dioxide, water, and sulfur dioxide all come out at different times in the GC. So you're able to tell how much of each compound you have. So it's separated by GC, gas chromatography, and then each component is measured with a thermal conductivity detector, which we're also probably going to talk about during the end of our semester, not right now. One thing that you have to know is that chromatographic separation requires that the entire sample be injected at once. You can't inject part by part of the sample, because the whole point of GC is to separate a mixture into their components. So if you actually inject things little by little, you're not, when you read your data, it's going to be wrong, because you have to inject everything at the same time so that the actual instrument can separate it for you. So that was separating at one time carbon, hydrogen, nitrogen, and sulfur. What about oxygen? If you wanted to analyze oxygen, that requires a completely different thing. You have to actually pyrolyze your sample. Pyrolysis is basically to decompose by heating, right? To thermally decompose your sample. And you pyrolyze it without adding any extra oxygen, obviously, because that's going to change your value of oxygen in there. But you pyrolyze it without adding any extra oxygen. And then those gaseous products are passed through a nickel-coated carbon at a really, really hot temperature to convert that oxygen from whatever sample you have into carbon monoxide. So oxygen analysis is the one that's a little bit different, because you can't analyze oxygen in combustion analysis, because you're using oxygen to actually react with those compounds to get how much carbon, how much hydrogen, how much nitrogen, how much sulfur, how much etc., etc., etc. But you can't figure out how much oxygen if you're adding oxygen, if that makes any sense. There is one more type of analysis, which would be halogen analysis. I would just read over that and make sure that you kind of understand it. Don't stress too much about it. But the most important thing here is how to do these combustion analysis problems, and also be able to explain what combustion analysis is and know the difference between combustion and pyrolysis. All right, guys, I will see you in the next video.